Hello and welcome to my channel again. So today's video's topic will be fine and hyperfine structure of hydrogen-like atom. Here we will only discuss about the single electron atom or the hydrogen atom, but we are saying hydrogen-like also because the Z we are not taking as equal to 1. Okay, we will take that under later approximations, but from the starting we will start from the Dirac equation. And in the Dirac equation there will be no mentioning of Z equal to 1 case. Okay, so here the point is why we need fine and hyperfine structure in the first place is because we know from the Bohr's theory that the energy of hydrogen atom is basically minus 13.6 by n square eV, and now we can understand that basically what happens. This is a very crude theory and the approximations are very crude. So when we are using say a very high-tech instrument where the single line can be split into multiples. Okay, so now we don't have any explanation why the lines are getting splitted when we are using a better spectrometer or a high resolution spectrometer. So to understand these hyperfine lines or fine lines, we have to understand the theory on a deeper level that was missing on the Bohr's theory. So here we will try to do that. The fine structure is not just basically for a single cause. We will have multiple terms in the Hamiltonian. Here we will talk in terms of Hamiltonian obviously because we are doing the MSc course here. So in the Hamiltonian we will get multiple terms, and for multiple terms there will be multiple corrections to the energy levels, and those terms can have magnetic field dependence or velocity dependence or spin orbit dependence or itself the kinetic energy dependence also. Okay, so in BSc courses what we often do is basically take the Hamiltonian by ad hoc manner and we basically solve it. But the problem is we know how to solve the Hamiltonian on the first place for say the Darwin term or the relativistic correction term or the spin orbit term, etc., or the fine structure terms also, hyperfine terms also, but we don't know the origin. Okay, here I will talk about the origin. Most importantly, I will solve the entire theory, but the most important thing that will be unique in my video is basically you will get detailed derivation or detailed explanation of the fact that how the terms are getting generated on the first place from the Dirac equation, because Dirac equation is the ultimate theory when we are talking about quantum mechanics, not Dirac fields but Dirac wave functions, or to be precise Dirac spinors, EC2 structures. This is the ultimate theory for fermions. So we will talk about the electronic structure of an atom in terms of Dirac's theory or Dirac equation. So now I will start with the Dirac equation. So as you can see, I have written the Dirac equation here in terms of alpha and beta matrices, and I have given a heading. I will erase it later because we will be needing space here. So after writing the Dirac Hamiltonian, what we will do, we will say we will apply a external magnetic field. Now as I said that there will be multiple contributions to the fine structure, so it is better that we take a magnetic field, and it is in our hand that we can switch off the magnetic field by taking the P equals to 0. So in the presence of an external magnetic field, our P will get modified as P plus EA by C. It is basically minus QA by C. So I have taken Q equals to minus C because we are talking about the electron. So it is P plus EA by C. Okay, and now what we have to do? We have to put this value in the Dirac Hamiltonian. So H Dirac. If you want to give a B external as an subscript, you can, for your better understanding. What I will do is C. This C is basically the speed of light, as you know, and alpha is our matrix, and with that we will put this value of P. So basically dot P plus A by C. Okay, and beta MC square as usual. Oh no, wait. There will be a minus E phi because it has an electrostatic potential also. Now, under radiation gauge condition, okay, these conditions are different names based upon different theory. Sometimes it is called Maxwell's gauge, sometimes it is called radiation gauge. Based upon the theory it is being used. Okay. Now under radiation gauge condition, we know that del dot A is equals to 0. Right. And phi also equals to 0. We will take. So what we end up with, I'm not writing the subscript again here. C alpha dot P plus A by C plus beta MC squared. Okay. You say this is our equation number 2. So now this was Hamiltonian. Now what will be the equation? What will be the Dirac equation? Time dependent Dirac equation. Time dependent Dirac equation is equals to C alpha dot P A by C plus beta MC squared. Okay. And here we will take, no, I will introduce it on the later stage, psi r comma t. This psi is not wave function. I think you know that, but still I am saying equal to I h cut del psi del t, where it is important to mention that psi, let's take the capital psi because we will take the small size later. Yes, capital psi is element of SU2. Okay, so it's basically a SU2 doublet. It's basically a SU2 doublet. Now, I will erase this portion. As we know that for stationary states, any wave function, okay, can be written as, if they are separable, obviously we have assumed that the wave function is separable into different coordinates, so we are applying that, and by applying it, by solving it, we will finally, because you know it is basically the BSc level problem, so I will not do it rigorously here, and e to the power minus I E N T by h cut. Okay. Oh, sorry, it is not quantum mechanics directly, so I will not put the n here. So by using the separation of variable, we have finally reached this. Okay. And after this, what we will basically do, we will use this equation in 2. Let's say this is 2a. Okay, we will use this 2a on 2. Oh no, sorry, this is 2. So let me say this is 3. Then this is not 2a, this is 3. Sorry, okay, make the numbering correct. So I will put 3a on 3, and what we will exactly get is C alpha dot P plus A by C plus beta MC square this whole thing and then multiplied with chi of r. I will omit this because now we are talking about time independent Dirac equation. Okay, this is what? This is time independent Dirac equation. Okay, we will get our necessary Hamiltonian structure by solving this. Okay, the time dependence is not basically necessary. The time dependence comes when we are interested about radiation. Here we are not talking about radiation. Here we will just talk about the transitions. So for transitions this is necessary and this is enough. And here I will like to say some structural constants, like what is alpha? We know alpha is basically 0 sigma 0. Okay, and beta is equals to identity 0 0 minus identity, because we know that trace of alpha and beta both are 0. Some properties that are known from the relativistic quantum mechanics. And to be precise, let me define a structure. So now as you can see that here I have no time dependence. This is positional, this P is positional, this A is positional, because the magnetic field is constant field. Okay, we have applied a constant field, we have not applied a time varying field. It is not necessary. And alpha beta are constant, so everything here depending upon the time is constant, and here only we have the positional dependence. So what we have chi as here, chi or jai, whatever you say, phi and psi. Okay, this is also a SE2 doublet, but depending upon r only. It has no time dependence because the time dependence was there and we have omitted the time dependence, and this is only the positional dependence we have. Okay, I hope you have understood till this part. Now we will just put the exact values here. Okay, I have no more thing to do here technically. So C, and we know the value of alpha, that is 0 sigma and sigma 0. These are 4 cross 4. Okay. So 0 sigma 0. I don't know if my letters are visible or not. I cannot see my screen from back, but please comment down if it is not visible so I can improve it. And beta, we know beta is identity 0 0 minus of identity. Okay, you can see that in every cases I am writing this as bold identity and not like 1. Okay, because it is not 1, it is a 2 cross 2 matrix. Okay, 2 cross 2 identity matrix. So for that reason be careful when you are using this kind of a notation here, because in RQM or this kind of theory where Dirac equation is involved, 1 is not basically 1, it means an identity matrix in general, because the wave function there is basically not a wave function, it is a spinor. So spinor means it is a SE2 doublet, and SE2 doublet has a matrix structure. You cannot write an identity or cannot write a 0 like this. Okay, if you are writing 0, you have to write 0 like in a bold manner. Okay, I hope it is clear. So I will get back to this one. This I have written and with an mc squared. And now as we are talking about time independent Dirac equation, extra central potential term I have to introduce here, because the electron and nucleus got some interactions and this interaction is missing here. So as now I have to incorporate the interactions, because it's a central field problem we are trying to solve, because every atom, if you see hydrogen or hydrogen like, is a central field problem. So we have to apply a central potential here. So V of R is representing our central potential. It is not related to some kind of an electrostatic potential or magnetostatic potential. Okay. So V of R, and here I will introduce another identity, because these are matrices and this cannot be a number or variable or something like this. It has to be a matrix structure. For that reason I have introduced an identity, and after this I will write my phi and psi, and this is equals to E phi and psi. Okay, I hope you have understood, and I hope you have already also understood this V of R. Okay, I have to introduce it. The reason for introducing this central potential is basically due to the fact that we are dealing with a system of atoms, system of atom with electrons. So there will be interaction between nucleus and the electron orbiting. Okay, so this is the reason of this V of R. It is very important to know each term of your solving equation, because sometimes in the question they ask you to explain the Hamiltonian. So you have to know that for which value, for which term you are taking, and this and that. Okay, so I hope you are getting it. So if you are done, pause the video, because I have to remove it. Okay, I'm giving you 3 seconds. 3, 2, 1, now. So as you can see that I have written the previous equation here, and now what we basically have to do is basically multiply the matrices, and we will get the terms those are required. So basically you can see at this position we have a mc square and a potential. So basically we will get mc square plus V of R, and in this position we only have sigma dot this quantity. So with the C, obviously, don't with the C. Okay, it is very important to remind every constant, because otherwise you won't get the necessary term, which we will be calculating on the next video. Let us write it in this manner: sigma dot P plus A by C. There is a reason why I am keeping the C here and not multiplying inside. So here we will also get sigma dot P plus A by C, and here we will get minus mc square plus V of R. Okay, I hope you are convinced with this matrices. And then phi and psi is equals to E of phi and psi. This is a small psi. It is not actually the capital psi. Capital psi has embedded structure, and inside that embedded structure these are two different structures, phi and psi. So this psi and the capital psi are different, not same. Okay, that has time dependence, and it has nothing to do with like this. And now we will see, if we multiply those like normal matrix multiplication and then compare, we can see that this quantity multiplied with this mc squared plus V of R is 5, then plus this quantity, that is sigma dot P plus A by C psi is equals to E phi. I am basically skipping a single step where I have to write this whole thing as a single matrix, and this is also a single matrix. So this is basically equal to this, like AB equal to CD, so A equal to C and B equal to D. So I am skipping the step here because we have to do a lot of mathematics here, and we will call it equation 4a. Okay, and similarly from here we can write sigma dot P plus A by C into phi plus minus of MC square plus B of R. Let us keep it in a bracket. Psi equals to E. This is 4B. Okay. Let me make sure I haven't done a mistake here. This. Fine. There is no mistake. Now I will define the, as we are now in the relativistic domain. Okay. So I will define that E is equals to some E prime plus MC square. What? Rest mass energy. Rest mass energy. Okay. So, sorry. E prime plus MC square. So using that, using E prime on 4B, what we will get is basically take this quantity on that side, okay? Right side. Sigma dot E plus A by C. C was there, yes, C was there, a phi, and this is equals to E plus MC squared plus V of R equals to psi. Okay. Now, if we try to solve this whole thing, let us put the E equals to E prime plus MC squared here. So this term will get modified as, I am not writing the whole term, like this part I will remove, and I will just write this part as E prime plus 2 MC squared plus V of R to the psi. Okay, I hope you guys are convinced with this. And so finally we can write that psi is equals to this whole thing will come as denominator. So sigma dot T plus A by C, okay, and the whole thing will be denominator as E prime plus 2 MC squared plus V of R, okay, and the C, and what are we missing? Something is missing, phi. Okay, so now we have a relationship, declared relationship between psi and a phi. So now to solve this further, what we have to do, let's say this is equation number 5, we have to put on 4A. Here I am changing the ink because a very important step is coming before I put it, like here, no, not here, we have to put 5 on 4A, but before that, we have to take the non-relativistic limit. Okay, we have to take the non-relativistic limit here. Now this is a very important step, because we have to understand that if we are starting from the Dirac theory, which is basically relativistic theory, then why we have to jump to the non-relativistic theory to go further? Why cannot we just solve using relativistic theory? And on the final step, I will just take the limit and I will get the final result as we are supposed to, or we are expecting here. But the point is that I have said earlier we will only be able to solve the hydrogen atom fine structure or the hyperfine structure using this theory. Okay, because the point is, we know, I mean, if you have seen my Runge length vector video, you already know that the z value of an atom can be highest 137, not more than that, because when the atomic number is 137, it reaches the velocity of light. Okay, the electron orbiting around the nucleus reaches the velocity of speed of light, which is basically the maximum limit we can get. After that, it will be an unphysical limit. So here for the hydrogen atom, what is z? Z equals to 1. I think you guys will remember that I said here I will not assume anything regarding z, but in the middle of the theory we have to assume to go further. Here is the point where we have to assume that z equals to 1. So basically we can say that if z equal to 137 is giving us the relativistic level velocity or velocity comparable to c, then obviously for z equals to 1, it is trivial to assume that the velocity will be very less than c. Okay, very less than c. So we can take the non-relativistic limit without distorting our theory or distorting our result. So under this approximation, we will do the binomial expansion. Okay, we will do the binomial expansion of this quantity, because now we can say that this 2 mc square is much better than wait a minute, something is wrong. Yes, this p, it will have minus in it. Yes. Now I think it's okay, because the plus p will get minus p when I change the sign. Yes, so e minus v of r, because in non-relativistic theory the c is basically tends to infinity. Okay, the c is basically infinity in the non-relativistic theory. So for that reason 2 mc square is far better than e minus vr. So now we can take the binomial expansion. How? Is basically psi is equals to c sigma dot p plus a c. And here what we will do, we will take the 2 mc square common out, and we will write that 1 plus e prime minus v of r. Have I written the prime there? Yes, that will be a prime. Please note that I might forget to put the e prime there. If I miss, it is always prime, because there is nothing we are doing in terms of e here. Okay. So this is 2 mc square. Okay. Now this thing can be expanded into a binomial series, and we will. Okay, let me write in the next step. Is this c and c square will get cancelled out, this and this will get cancelled out, and finally we can write that 1 by 2 mc 1 minus e prime minus v of r by 2 mc squared, then sigma dot p plus a by c. Okay, this is psi and this is phi. So instead of putting 5, now what we will put? We will put 5a. So let us modify this as 5a. So we have to put 5a on 4a. Now I will do that thing after I erase the board, so you can pause the video. I will give you another 3 seconds, obviously, so pause the video, and I hope you have understood in this. So I will erase the board in 3, 2, 1, now. Okay, so as you can see that I have written the thing what I am going to do, and the equation I have not erased it, because I think it will be easier for us to do the job. Because what we are going to do next is basically take this whole thing on my right, and we will end up with sigma dot c sigma dot p plus a by c. Okay, and with this whole psi thing right there. So now I have got 1 by 2 mc. Okay, I have taken the constant term out here, and as it has an r dependence, see, it is very important here. It has an r dependence right here. Okay, so I cannot take this beyond this. Okay, I have to keep the right term here because this is quantum mechanics, not classical, and we don't know if the potential and the kinetic energy basically exchange, not kinetic energy but the momentum are basically exchangeable or they commute. Okay, we don't know, so I will have to keep it intact. In classical mechanics we can do that. In quantum we don't know if they commute or not, so it is safe to keep our things like this: sigma dot p plus a by c and phi. Okay, now I have written only this term. Okay, now this term is now this big. Okay, but don't get scared. This is very easy to do. And now we have E minus mc squared minus v of r as phi. So E equal to E prime plus mc squared. So this is basically E prime. Okay. Hope I got everything correct here. This is personally my favorite calculation because here you don't have to assume anything. Obviously you have to assume the non-relativistic limit because otherwise the theory is irrelevant to your system. But without that consideration, everything is coming from a scratch, which is the most fundamental equation known to humankind for many particles in quantum mechanics. Obviously it is Dirac equation, and if we take the phi naught and omit the probabilistic interpretation and make the coordinates as this parameter, then it will become our field. So now we have the Dirac field, and using the Dirac field we can solve the QED. So I think this is the most beautiful theory I have ever seen in physics. But obviously you can only solve QED using quantum field theory, and the rest problems are huge. So this C and C will get cancelled out, so I will end up with the 1 by 2 m. And now as you can see that there is a point why I kept the C's instead of taking those inside. And this term you can see I will only take the terms that has 1 by c or 1 by c square dependence, not more than that, because under non-relativistic limit we have already seen that c goes to infinite, so c is a very large number. But if we don't take the c square term, then we will not reach our goal. Okay, because let's say if we avoid the perturbation, then what is the point of doing the whole theory? So we cannot avoid it. Okay, we have to keep it, the first perturbation term we have to keep, and the rest we will ignore, like in physics we always do. So what we have to do, we will ignore all the c cube c to the power 4 dependent terms and only keep the c square terms. So c or c square terms. So it is basically 1 by 2 m. Inside a curly bracket we will write sigma dot a by c, and this, because I'm multiplying, okay, multiplying with this identity. Sigma dot, you can write an identity, p plus a by c. Okay, I hope you're convinced with this. And now what you have to do is this: sigma dot p plus a by c, and this whole thing minus is on the side by 2mc square, and then also sigma dot p plus a by c. Okay, you have to work very hard to get the actual Hamiltonian, and we will not do that in a single video. Okay, I will end this video by a turn where we need to directly simplify it, because it needs more simplification where we can actually distinguish the terms. Okay? I will end today's video there. 1 by 2m. Now we already know that there is a formula that sigma dot A, sigma dot B, both are vector quantities, is basically A dot B plus I sigma dot A cross B. Okay? This is the identity known to us. Okay, we have done a lot of quantum mechanics and we are already aware of this. So I will directly use this without proof, and it is not necessary to derive this whole formula here too. So 1 by 2m. So this is basically P plus A by C whole square, because this dot this is basically the same, because P and P commutes, A and A also commutes because it is abelian base theory. Okay, and after this we will write plus I sigma dot P plus A by C, P plus A by C cross P plus A by C. Okay, so this term is sorted minus. Now I will only take sigma. I will only take sigma P and sigma P here, because if you take this term, it get multiplied with this, you will get a C cube. Okay, if you take then this term, it won't matter, but it will remain the C cube. If you take this term, it will get C cube, and if you multiply it again this A by C, it will get C to the power 4. And according to our assumption, we have already told that in our theory we will not take any term regarding C to the power 3 or C to the power 4. So this term will reduce to sigma dot P T prime minus B of R by 2mc squared. I hope I'm doing everything right. By 2mc squared. Yes, fine. Now what I have done, I have multiplied this 2m everywhere, so I have to write a 2m here and 4m squared c squared here. Okay, and then sigma dot. The curly bracket was missing, so for that reason I was thinking why the curly bracket is missing. Okay, now further simplifying, if you open this term 1 by 2m, P squared plus E squared A squared by C squared plus let me write it directly. I will multiply the 1 by 2m directly. Okay, it's not necessary to do all these irrelevant steps. P squared by 2m plus E squared A squared by 2m C squared, okay, plus EA by MC, okay, and there was a phi. Okay, there was a phi. So if the phi is there, then here is a phi 2, here is a phi 2, and if we keep this term in a square bracket, here is a phi 2. Okay, so A dot P, and here we have phi 2, phi and a phi. Don't miss the phi. Plus, now what is P? In quantum mechanics, what is P we already know. P is basically minus I h cut grad or del mu in this region mu, and if you remove this, in this I h cut grad. So basically I will take the grad here and take the I h cuts out. So what we have here is basically I by 2m I h cut by I e h cut by c as common, here and here common, and then grad cross A plus A cross grad. Okay. Now what we basically have to do is this phi, and can we simplify this? Yes, we can. Minus 1 by 4 m squared c squared, keep the minus here, this minus I cut will get squared because from this we will get twice, and sigma dot grad E prime minus V of r by nothing, so we have taken it out, E prime minus V of r, then sigma dot grad again with a phi. Okay, I hope this is convincing to you. And after that, what you basically do, we'll just remove the signs from here. So what we had here is basically this. What we basically had here is basically this. E prime minus V of r, okay, phi, it is equals to this whole thing, okay, and here I can take an approximation that this term as a squared goes to 0, okay. How you can show this? Because we know that under constant magnetic field, under constant magnetic field, A equal to minus R cross B. Okay, I think there is a half factor, half R cross B. So put this there and you will get a 0. Okay, put that and you will get a 0. And we will use this condition here also, or here also. Okay, the terms these are coming dependent upon A. We will use this, but on the next video or the next after next, I don't know, the third video I guess. So yes, this term was on the left, and on the right it was p squared by 2m phi plus E A dot P E by MC A dot P phi minus this I and I will give you a minus H cut E by 2MC. What I have here, del cross A plus A cross del. Okay, and after finally this, we have I square equal to minus 1, we have minus square equal to plus, and we already have a minus, so we will get a plus sign. Okay, h cut squared by 4 m squared c squared sigma dot grad, then this whole thing E prime minus V of r sigma dot grad of phi. Okay, so this is the final equation. I will end my video today. Okay, and let us give this equation number 6. I think I have used 5 somewhere, and if I haven't used it, give this as 5. Okay, if 5 is used, then don't. If 5 is not used, give this as 5. Okay, so this is my final equation for today's video. Now on the next video, what we will basically do, we'll take this term on this side and define this as the unperturbed Hamiltonian. Okay, and this term we have to simplify, this term we have to simplify, and this term, most importantly this term, put a star over there. Okay, this term we have to simplify a lot, and we will get the final Hamiltonian on the next class or the next video. So I hope you have enjoyed this mathematical joyride, and thanks for watching. If you like this video, then please share with your loved ones and subscribe if you are hoping to get videos like this, and thank you.